Okay, good morning, everyone. Let's get started. Welcome to EGR 685. So today, the first speaker for this course, 2024 spring, is Ali Raza. Ali Raza graduated from my lab from Central Michigan University a little over a year ago, and he had been working in Toyota, Kentucky for about a year, and now he's in a transition phase to move to another job. So I requested him to come over and give us a talk on his work, machine learning in additive manufacturing. So without any further delay, Ali, the floor is yours.
Thank you so much, sir. I will be talking about the usage of machine learning in additive manufacturing, but just to add to the introduction that Dr. Hayter gave, I am actually a materials engineer. I completed my bachelor's degree from back home in Pakistan, and since I had an enthusiasm for working in the industry, so I worked in a couple of industries like the Chenab engineering back home, and then I had an internship at Porsche. And these are the things that actually increased my interest in working for the industry. So here I am sitting at the University of Cambridge in a conference with one of my other professors in 2018. And that's when he pitched me the idea that if you really want to pursue this dream of yours of working in the industry, you really have to go to the USA. So thankfully, I was able to secure a teaching assistance scholarship with Dr. Hayter at Central Michigan. Fast forward 2 years, I graduated last December in 2022. And then, like Dr. Hayter mentioned, I worked for a year in the production sector of Toyota of Kentucky. So just a little bit of introduction of myself. So now we're just smoothly going to move towards the actual point of our discussion, which would be additive manufacturing. Now, before we dive into the actual idea of what it is, let's talk about what is the initial perception of additive manufacturing. So, the initial idea is that it is just a manufacturing process that decreases the product development times and decreases the costs associated with that as well. But as the years go by and as the technology develops, we see that now we're able to answer three F's. So, first of all, what type of shapes and dimensional tolerances can we have? That answers the form. And once we have that thing, once we have an actual part that we built, will it even fit our assembly or whichever part or whichever item that we're trying to make? And once it fits, does it even function in the intended way that we want it to function? So these are some of the things that we have been able to answer as the technology has grown into its current stages from its early introduction in 1980s. But where exactly did it begin? It was actually in 1986 when Chuck Hull was given the patent for the first form of 3D printing, which was the stereolithography. You can see the image on the right side. But it wasn't until 1999 that this technique was actually used for any practical purposes, and it was almost in 2014 when it was used for an engineering application where the first 3D printed car was made by blending ABS and carbon fiber by the company called the Local Motors. But what we're interested in is the huge development in 2016 when the first kidney, as I have shown in these two images on the bottom right, when the first kidney was actually 3D printed. Now, when I say 3D printed, so 3D printing and additive manufacturing, they're just like synonyms. So that's what happened in 2016. And now, if we look into the engineering applications, we just find that Bugatti became the first car manufacturer to use 3D printing as the method of manufacturing for the brake calipers for the world record holder car, the Chiron, as I've shown on the picture on the top right. Now, what's interesting about this car right here is that this part right here, this brake caliper, this intricate designs and all these channels and all these sections and the hollow areas that we see, all of this was possible by using the 3D printing and the dimensional flexibility that we get from it. And of course, we were using the hollow sections of titanium, as I mentioned here. And all of these things gave rise to unbelievable physical and mechanical properties, all of which were evident in the high-speed runs when they saw that the brake calipers as well as the rotors did not fade or did not fail or were up to testing temperatures of 1200 degrees Fahrenheit. And of course, these type of things led to the vehicle going to the high speeds of almost 500 kilometers per hour. And this car right now is in the Guinness Book of World Records just because of this dependence on the braking power provided by these calipers that were made by 3D printing. So just another example how these things are affecting the engineering sector as well. But now some of you might be aware of the idea of this technology, some of you might be new to it. So let's just run swiftly through the idea. So simply put, it is just a direct fabrication mechanism in which we make a 3D model, a CAD model, through a computer of whatever part we need to print. And then that model is supplied to a computer, which is connected with the actual 3D printer. And then the 3D printer, what I've shown right here. So this has high-speed lasers in it. I will explain the whole process one by one in the next slides. But just to summarize, what happens is that the high-speed laser starts to melt the uniform layer of powder that is deposited on this build platform right here earlier on. So once that initial layer is melted and solidified, then the laser beam moves a little bit overhead, and then it builds the second layer, and then the third, and then the fourth, all the way upwards up till the last layer, and that's when we see that the final part has been built. Now, the build can be vertical or it can be horizontal, but let's just go a little bit deeper into the actual process. So, like I said, the first thing we need is a 3D model through a CAD modeling system. So we're already aware that there are different types of modeling mechanisms. So there are two different types that I want to discuss here and why we need the latter. So we have the solid model and then we have the polygon model. So the thing with these two is that in case of a solid model, we can have walls of zero thickness as well. Now, this type of modeling is very useful if we are looking for gaming graphics or gaming scenarios. So once we have that, and I've given an example of just a random example of a pair of spectacles here. So this is an example of the model that we need. We'll have to go to the previous slide, sir. Yeah. So once we're done with that, so we need to convert that model into a format that is readable by the 3D printer itself. And that is when the conversion to STL comes into play. Now, STL is nothing but an abbreviation of stereolithography. Some people also call it standard triangle language. So what it does, it just defines the 3D model into a 3D shape with all the intricate details that might be present onto the surface and that might not have been visible in the initial model. So once we have that, we just apply that to the 3D printer. The 3D printer already has the micron-sized metallic powder. It could be titanium in case of a Bugatti. It could be stainless steel. It could be anything. And then we have a high-speed laser. So the first step is that the build platform is actually covered with a uniform layer of all the powder, and it covers the whole platform. And then when the laser fires up, it starts to melt that first layer of powder in accordance with that coordinates that we have provided in the model. So let's say the first layer has been molten, it starts to solidify, then the hopper, which contains then the actual mechanism of the laser, it moves upwards by a certain dimension. And then it starts to deposit and melt another round of powder. It deposits the powder, it melts the powder, it moves upwards, so on and so forth. It's a cyclic process, 1, 2, 3, all the way upwards to however many layers need to be deposited up till the part is finished. And now it could be a horizontal build, it can be a vertical build, but most of the times people prefer a vertical build. So once you're done with that, you just have to remove the part, and if you see this image right here, you can see the image on the extreme left here, you can see these little edges between the notches of this part here. So these are called the supports. So these little things are actually responsible for making sure that the part is standing upright onto the build platform. So obviously they're not part of the actual component, so you have to remove them. So you see that on both of these next images right here. So sometimes there's just standard support, sometimes they're dissolvable, so you just put them in a solution and they just dissolve right away. Otherwise, you have to use mechanical methods like grinding and polishing, and you're good to go. And that's the beauty of this process, because once you do the 3D printing or additive manufacturing, you are literally facing little to no post-processing. Don't get me wrong, there is still some type of post-processing associated with the mechanism, but not as extensive as we have with, let's say, casting or forging or welding, all these things. And this is where we gain an edge over other conventional techniques. We're talking about the benefits, right? So let's just talk a little bit more about them. So I've already talked about the shape tolerances, the dimensional flexibility, and the way we can just customize whatever we need. Just if you imagine the type of intricate details you have on that brake caliper, you are literally amazed by this technology. It just goes to show that how much flexibility we have and how much we have come far from the conventional techniques like casting or forging or all these other techniques. But we have all these math customization techniques nowadays. And of course, once we do that, we have little to no material loss because we're just making a simplified model and we have no other excessive parts associated with that. Like, for example, let me talk about casting. I have experience of, I have a little bit experience, like a year and a half in the casting industry from back home. I promise you, every single day I used to see parts which had to be grinded just because they had excess metal coming out of the molds. They had metal just splatters all over the place. They had shrinkage. They had porosity. So all of these things, what are they? It's just a material loss, right? But this is something that you will never see when you're using additive manufacturing. Mind you, there are some defects. I'm not just going to talk about all is well and you're in a utopia. You're not. Obviously, there are some defects associated with everything. And yes, there are defects associated with the additive manufacturing as well, but now is not the time to talk about it. So we just move towards the cost associated with that, and the lead times and the times that you can make a part. And then another thing that I found really interesting are these acronyms. So let's just talk about casting or forging. I'm not sure how many people are familiar with the casting and forging mechanisms, but in casting you have to make a mold, and in forging you have to install huge, gigantic 8,000 tons, 10,000 tons, huge dies, and it's a big cost to replace them. So whatever you see is what you get. So this WYSI is what you see is what you get. So whatever you see, whatever you've built, that's what you're gonna get. You take it or you scrap it. You cannot edit it. But the beauty with additive manufacturing is that how do we start the whole process? We just make a simple CAD model. And tell me how hard it is to edit a CAD model or make a new one. That's why this beautiful acronym associated with the additive manufacturing, where we see what you see is what you build. So they needed a very unique form of a caliper. They just saw it and they just built it. They want these very tiny gear assemblies in all these chronograph luxury watches like Tag Heuer and all these things. How do they make them? Do they cast them? Do they make them with conventional methods? No, they just use 3D printing because all these little parts, all this flexibility wouldn't have been possible if there were no 3D printing. So enough of 3D printing. We're just going to move slowly into the second part, and that is machine learning. Now, this is a hot topic for the past couple of years, and so I honestly don't think I need to explain this to anybody, but let's just look into how people have been explaining it in the past. And the simplest words are people talk about automating the automation so that the computers just do the work by themselves. And now, believe it or not, this is something that we have been doing pretty much all our lives. And I will give you just one example here. So you just feel like listening to some music and you say, okay, I'm just gonna go to the YouTube and I will move and listen to some, let's say, for example, I will listen to some trance music. So you just search for a track and then you just listen it. And you just close the whole thing and it goes away. And the next time when you open the YouTube, what do you see? There is a new trance track in your suggested track. So what is it? So little did we know that this was just another form of machine learning that we never paid any attention to. So this is just one example. And of course, then we have the machine learning that we see when we type anything on Google, and before we even finish the words, they're actually finished for us. So this is also a type of machine learning. But for people who have little to no experience with machine learning, let me break it down. It is more like gardening, where you are the actual gardener. And what you do is that you just plant the seeds, which are, in this case, algorithms. Once you've planted the seeds, you actually supply the data to the algorithms, which is what we can talk if it like nutrients. So you supply the nutrients to the seeds, the fertilizers, that is your data. So you supply the data to the algorithms, and in return, you get plants, which in this case would be the program itself. But how does it actually differ from traditional programming? The traditional programming, on the next slide, please. So if we look at the next slide here, we see a comparison between the traditional programming and the machine learning. So what we see here is that in traditional programming, what we do is we have the data. Now, it could be any type of data. I'm not being specific here. It could be any type of data. And then we have a program already set. We supply both of those to the computer, and then it supplies us with the output. When we talk about machine learning, obviously we need to talk about learning. What exactly are we learning? We're learning a task. So what could that task be? And for that learning task, I'm just going to give you a simple example from Tesla. Now, all these new cars that we see, the Model S, the Model P100D, all these vehicles that we see from Tesla, they're equipped with something called the autopilot. So, what we need that car to do is drive itself on a 3 or 4 lane highway without crashing, right? So that is called the task. Now, once we have this task established, how are we going to measure the performance? Now, the performance of the car is measured based on the number of miles that the car drives without crashing into anything, or without making a mistake, or without swaying out of the lane. This is called the performance. Now, for example, we've been hearing a lot of backlash on this same method of Tesla, the autopilot, where the cars are like literally going out of lane and swerving wildly and then turning even when the driver doesn't want the car to turn. So what is it? What does the car need? It needs experience. So for example, if you're sitting in the car and your Tesla just swerves wildly to the right or left, what are you going to do? You're just going to jump in, and then you're going to try to correct the mistake, make the car go straight again. And at that time, the machine learning algorithm, which is in the computer system of the car, it starts to gain experience. Okay, I was just about to go out of lane, and the user just brought me back into the lane. That's when the algorithm is using all this data, how to stay between the two white lines, and it's gaining experience. And that, in a nutshell, is what machine learning is. So, another example. There are actually different types of machine learning. So I'm just going to give you another example which is called the basket analysis on the next slide. So this is another technique that we see pretty much every day, but little did we know that it always employed machine learning from the very start. So you go to the supermarket, and what you're doing is you just go into the section to buy some crisps. You're seeing Doritos, Lay's, and whatever. What do you see beside all that chips section? You see mayo dips. You see different kinds of dip. You see jalapeno dips. Okay. You go to the milk section. What do you see alongside milk? Just alongside milk, or just in your eyesight, in your vision, you see eggs. So why are they strategically placed like this? So all these supermarkets, they use machine learning algorithms to collect the data of all the sales, that whoever goes in to buy some milk is definitely going to go and buy some eggs as well. And even if they're not, they strategically place the eggs closer to the milk and all the dips closer to the crisps, so that if a person goes to buy one item, he can buy the other item on impulse as well. And this adds to the data set. And that data set is used in the machine learning algorithm to just increase the sales and just set up all the systems. You will never see, if I ask you a question, you will never see engine oil placed beside the bread aisle, will you? Of course not, because those two never make sense. And you will never see bread in the clothing section. Of course you won't. So these are the things that employed machine learning all this time, but we never knew about it. So we move to the next slide here, and now this is another example of machine learning called the classification technique. Now, this is another technique which uses classification. So, for example, I am just about to go and take out a car loan or a car lease. Obviously, they're going to look at my credit score. And when they look at my credit score, what they're actually doing is that I go and I just give my credit score. They look at my credit history. They qualify me or disqualify me. Then, of course, then another person goes, then another person goes. Some people get accepted, some people get rejected. But all of this data is being compiled in the data set of whatever bank or whatever car dealership we walk into. And that is being used to train the future machine learning models. So what they do is that, for example, if I'm going and I'm asking for a car loan, what they're going to do is they're going to look at my position on this chart right here on the bottom right. So what they do is they see my position on this chart. So if I have a high income and I also have a high saving, so that would mean I'm a low risk individual. So that would mean I will be easily paying off that loan back, and that means I'm a low risk individual. So, but if I have a low income but high savings, that still makes me a high risk individual, and that leads to obviously a rejection. So the point is not to discuss about getting accepted or rejected for a car loan. The point is that all of these acceptance and rejection and all the criteria that led to the acceptance and rejection, all of that is being saved. It just doesn't go away. That is being used as an experience. I was talking about Tesla, right? So it was gaining experience in a different way. But here, all this data is termed as experience. It's going into the data set, and then next time anybody walks into the dealership to get a loan, that experience is used to predict whether or not that person is qualifying for a loan. So really interesting mechanisms that we see. Another thing that I saw, I was trying to keep it short, but this was such a beautiful example of machine learning that I couldn't just skip it. And that's called reinforcement learning. We all love dogs, right? Okay, so what do we see here? So let's just consider that the dog is an agent, and we see that the dog starts to waggle its tail, gets excited, starts drooling as soon as it sees food. So what is it? It's called an unconditioned response. So, for example, if we just take the food away and start to ring a bell, what is the dog going to do? It doesn't have any food. It doesn't have any relationship to the bill. It's just going to sit quietly and it's going to wait for the food. So what happens if I just ring a bell and give the food to the dog? The dog will have whatever it needed, and it will just start waggling its tail and drooling all over you because it's got the food. It's got the reward, okay? But what happens if I take away the food, which was the reward, and I keep the environment the same? So I ring the bell, which is the environment, but I take away the reward. Now what the dog has in his mindset that, okay, the bell is ringing. The last time the bell was ringing, I got food. So this time the bell is ringing, but I don't see food. But what does that mean? It has reinforced in its mindset that the bell is ringing, the food is about to come. And that is how they just program their minds. And that's how we just simply say, oh, your dog is well trained. So what does that mean? This is just a simpler way of saying that it's reinforcement learning that is going on. Now we move towards the conflation of machine learning and additive manufacturing, whereby we see all these examples where we're using additive manufacturing and machine learning in parallel. Now, they're used in medical industry, we're using them in tissue engineering, like you saw that kidney being printed in 2016. So that was 2016. So just imagine what the world is doing in 2024 by this conflation. And of course, we have the building and infrastructure. I'm not sure if you guys have heard, but I was just reading an article whereby in California, they're 3D printing houses at an extremely cheap price. Just make the whole thing like 10 times, 50 times larger, and they're making all the layers, all the intricate walls and designs, and all the curving sections of the walls and the roof. All of those are being printed with 3D printing. But of course, there is no metallic powder in that. They're using liquid concrete that pours out of the spout, and then of course it moves as per the 3D model of the house. So just look at the extent to which we're going with every passing year in this technology. So let me just give you another example. We're talking about conflation, right? So this is from a research article that people actually worked on. So they were talking about using machine learning models for a smart factory. So the reason they call it smart factory is that, let's say we have a factory and it has multiple 3D printers sprawled all across the factory, and we need them to communicate with each other. Why would we want that? Now, this why will be answered later on with these 4 bullet points here, but let me just talk about something else before that. Now, there are 2 different types of training mechanisms. There's the offline model, and then there's the online model. So what these researchers did is that they used the offline training of the model. Now, the thing with offline training is that you supply the model with certain quantity of data, and then you do not supply another batch until you have an actual result or an output. Now, this is different from online model, in which you continuously supply the data as we go along making predictions. But they used offline training, and what they did is that they used the offline training by using previous data from all these 3D printers working separately, and then they all submitted or used that data as an input for that machine learning model, and all of that data was used for the main server. So what they found out is that when all these 3D printers are connected to a machine learning model, and then they're taking all the experience, like I said, from that machine learning model, they're able to self-organize. What do you mean by self-organize? By self-organization, I mean that the 3D printers are able to communicate with each other. They're able to manage their parameters. They're able to increase or decrease or edit the parameters as per the demand of the build. Of course, they were able to get information on the workpiece as well. Sometimes, obviously, everything is not 3D printable, obviously. So even this thing was possible when they used the machine learning for the smart factory, that the machine learning model would supply all the data to this server right here, and then the 3D printing mechanism would decide if the part is able to be 3D printed in the first place. If it's not, they won't fire up, because what they're doing is they're looking at the previous data that we supplied. So that is the type of information in workpieces that was really helpful. And of course, there was communication between all these machines, and then there was a real-time capability that if we find a defect in one of the parts that is being made in a 3D printer, it could just detect the defect and then of course take appropriate measures to correct that. Like, do you remember I talked about editing all the or managing all the parameters? So just by modifying or controlling the parameters of the 3D printers, it gained the real-time capability, and that's how it decreased the number of defects. So moving on to the final stages, we run into a problem. So the problem is, once we have finished with the 3D printing mechanism here. If we look at the top left, this image right here, so what we see here that we have a final product, but it's a rigid, static product. We can use it, and if it breaks down, it breaks down. You have to print something new. You cannot mold it. You cannot have sensory feedback from it. Now, this is a keyword that I intentionally used here because this is where people have started working into 4D printing. Now, this is still in the research phases. So what it does and how it's different from 3D printing is that we have a fourth dimension, which is called a stimuli. Now, those stimuli, as per the research, could be multiple. It could be temperature, it could be pressure, it could be pH. So these are the most major stimuli that we can use. And for that, we can just take an example in this image. And then, of course, I'm going to give you an example from BMW itself. So what happens is that, for example, if we have made this rod right here. So if we made it by 3D printing, we just made a rod, we're done with it. If it works perfectly, we're good. If it breaks down, if we try to bend it, it breaks down. We have to do something else about it. We have to edit the parameters or we have to make a new product. But if we use 4D printing, we add the stimuli of pressure and something called the shape memory. We use a certain type of material, a shape memory alloy, in the 4D printing mechanism, whereby even if we have a certain pressure applied, that would mean that the part does bend, but then of course due to the shape memory effects, it would just reverse the pressure and come back to its original shape. And these are some of the benefits that we might get from the 4D printing. And the reason I just highlighted the might is that all of this is still in the research phase. And of course, BMW being a pioneer in the automotive manufacturing, they're already working on a vehicle, still in the concept phases, obviously, whereby they have designed the body with a specific type of silicone. So the body is made of a certain type of silicone. So if you look at these unique wheel arches, so what it's supposed to do is that as you go on high speeds, the wheel arches would flex to increase and improve the aerodynamic performance. And of course, the material itself would behave in such a manner. And how would it do that? Because of course we have the fourth stimuli. But like I said, these things are still in the very early research phases. And but still, obviously, if you look at 1986, when the 3D printing was originally invented, and you look at 2024, just look at how far we have come in just 4 or 5 decades. So there's always hope for more innovation in the next years to come. But with that, I would like to thank you all, especially Dr. Hayder, for giving me this opportunity. It was really an honor for me. I mean, studying with Professor Hayder and then eventually coming as a guest to present in front of you guys, it really meant a lot. Thank you so much.
Okay, let's thank our speaker. Thank you, Alim, for providing the wonderful presentation.